In this lesson, we're going to examine games where players have continuous or infinite move spaces. Remember from last lessons, such as the matching pennies example or the prisoner's dilemma example, players only chose one of a finite set of actions. For example, in the prisoner's dilemma, they chose to either cooperate or defect. In this lesson, we are going to learn what happens when players can choose among an infinite number of actions. As noted in the lesson notes, this lesson does require calculus, but those who have not yet been exposed to calculus can skip this lesson without sacrificing understanding of any future lessons. So, the name of the game that we are looking at is borrowed from economics, and it is called Cournot Competition. So the story behind this game is that there are two firms selling an identical product. I know they're not the same, but you can think of it as Apple and Samsung possibly selling smartphones. Yes, there are differences, but for our case, we can just assume that they're the same product. So first of all the firms do is they choose their quantity. How many are they going to make? Once they choose how many they're going to make, the market clears such that all of the quantity are sold, and what adjusts is the price. So for example, in a standard economic argument, if a company wants to sell more of its product, they need to lower the price in order to sell more product because it entices more people to buy. So we have two firms, and they choose Q1 and Q2. These are what I'll call the choice variables. How are the prices determined by the quantity? So we make a very simple assumption, and we say that the price that each product sells for is equal to 100 minus Q1 minus Q2. So what this says is that the more that of quantity 1 that firm 1 produces, the lower the price will be, and the more that firm 2 produces, the lower the price will be. We can see, for example, if firm 1 chooses 1 and firm 2 chooses 3, it's 96, that's the price. If firm 1 chooses 10 and firm 2 chooses 20, we see that the price is now 70. Okay, so this is how the price is determined. We also have these, we will call them parameters, C1 and C2. These are called cost parameters. So C1 is the cost for firm 1 to produce 1 unit of Q1. Now what do firms want to do? Firms want to maximize their profits. So we can write the profit function like this. So the profit to firm 1 is a function that takes as an input Q1 and Q2. And the function looks like this. Okay? Remember, this term is the price. This is the quantity, and this is going to represent total cost. So, what this says is that a firm's profit is the price times the quantity, which is known as the revenue, minus its total cost. And firms would like to maximize this. So firm 1 is going to maximize this, and firm 2 is going to also maximize his profit function. So, recall from calculus, how do we find the maximum of a function? Well, to do this, we take the derivative and we set it equal to 0. So, we can say the derivative of firm 1's profit with respect to the quantity, Q1, is equal to, we can do the same thing if we were to write out player 2's profit function and his conditions. Now, both players are making a decision. So, if player 1, looking up here, were to know the quantity that player 2 were to choose, he would simply be able to solve for this equation, set it equal to 0, solve for Q1, and find the quantity that maximizes his profits. But you can make the same argument for player 2. If player 2 knew what player 1 was going to do, what his quantity 1 was going to be, he could again set this equation equal to 0 and solve for Q2. Turns out though, players don't know what the other player is going to do, but remember the definition of Nash equilibrium. It is such that no player has an incentive to change their action given what the other player is doing. So what does that mean? That means that both of these equations need to be satisfied simultaneously. Now, the rest, to find the Nash equilibrium, is just a little bit of algebra, but we can go ahead and go through and do it. So these are the two conditions that need to be met such that both players are optimizing. Again, remember the definition of a Nash equilibrium is an action such that both players cannot do better by changing their action. Okay, so what does this say? If we solve for Q1, so this implies that Q1, we will call it Q1 star because this is the equilibrium, must equal 100 minus Q2 minus C1 over 2. And we can do the same thing here. Okay. Now to solve, all we have to do is plug this into here, and then we can get the Nash equilibrium quantities. So let's do this. Okay, so after plugging in, we get this equation. We see there's a Q2 star on both sides, but now all we have to do is solve for Q2 star. So we can go through and solve, and we get Q2 star is equal to 100 minus C2 plus 2C1 over 3. So this is the Nash equilibrium quantity for player 2. And we can do the same thing by solving the equation for player 1. So this says that the Nash equilibrium strategy for player 2 and player 1 is a function of each individual's cost parameter, C1 and C2. In other words, given C1 and C2, for example, if C1 and C2 are both 1, we can find the Nash equilibrium strategies for player 1 and player 2 such that, given what the other player is doing, neither player has an incentive to change its quantity. This is a Nash equilibrium in a continuous move game.